All right, today we're going to talk about something you've probably heard of, the Nash Equilibrium. It sounds complicated, right? A big idea from economics, but we're going to skip the scary math because hidden inside is this simple, really powerful geometric idea. And once you see it, it changes how you look at, well, pretty much everything. Let's get into it. So it all starts with this question that I think we all wrestle with. Why is it that sometimes, when every single person makes the smartest possible choice for themselves, the whole group ends up in a complete mess, you know? It feels like a paradox, and it's right at the heart of what game theory is all about. And you really can't find a better example of this than the good old prisoner's dilemma. So imagine this. You and your partner in crime get caught. You're in separate interrogation rooms. The cops come to both of you with the exact same deal. You can either stay silent and trust your partner, or you can betray them. This grid here shows you all the possible outcomes, measured in years behind bars.
Okay, so let's just think through the cold, hard logic from your point of view. First case, your partner stays quiet. What should you do? Well, you should betray them. You get 0 years, you walk free. That's a no-brainer. Second case, your partner rats you out. Now what should you do? You should still betray them, because 5 years in jail is a lot better than 10. So here's the kicker. It doesn't matter what the other person does. Your best, most rational move is always to betray.
And of course, your partner is just as smart as you are, so they're in the other room running the exact same calculation. They also decide to betray. So what happens? You both betray each other, and you both get 5 years. And that's the whole paradox. If you had just both kept your mouths shut, you would have only gotten 1 year each. Both of you acting perfectly rationally led to a terrible outcome for both of you.
For a long time, people just saw this as a weird logic puzzle. But then this incredible mathematician, John Nash, came along, and he just looked at the whole problem differently. He saw something else going on entirely.
What Nash did was totally revolutionary. He said, hey, let's stop thinking about this as a puzzle where you're just trying to find the best move. Instead, he asked us to imagine it as a kind of geometry problem. The real goal isn't to find the best move, it's to find a point of stability.
And that point of stability, that's what we call a Nash equilibrium. Think of it like this. It's a state in the game where every single player has picked the best possible strategy they can, considering what everyone else is doing. At that specific point, nobody can do better by changing their mind on their own. The whole system is just locked in. Now here's the truly mind-blowing part. Back in 1950, Nash proved that these stable points aren't some rare fluke. No, they are a fundamental, unavoidable feature of every strategic game you can imagine. Every single one has at least one equilibrium point. It's like a law of nature for strategy. So, if this is all about geometry, what exactly is the space we're talking about? What are we measuring? Well, this gets us to the absolute core idea of this whole explainer. The space for navigating is a landscape of regret. And the goal is simple. Find the point where your regret is as low as possible. And let me be really clear here. When we say regret, we're not talking about an emotion, that sinking feeling. Not at all. This is a hard mathematical value. It's the literal distance or gap between the best possible thing that could have happened for you and what actually happened. It's a pure, cold measure of a missed opportunity.
Okay, I know, an equation. Don't panic, you don't need to solve it. The only thing you need to see is what this equation tells us. It creates a direct link between the regret of a choice, that's our little d squared right there, and how likely a rational person is to make that choice. Basically, the more regret a choice has, the less likely anyone is to pick it. It's that simple.
And that right there leads to the big aha moment. This is what it's all about. In this geometric world, a Nash equilibrium is simply the point, the one spot in the whole game where every single player's mathematical regret is 0. Everyone is making their absolute best response. There are no missed opportunities left on the table. Nobody wants to move.
So once you start to see the world this way, as this strategic landscape of regret, a bunch of other complicated ideas in game theory suddenly become way easier to understand. Let's see how this geometric view helps us make sense of how players learn and adapt over time. I mean, how do people even find this equilibrium point? Well, you can picture it like a ball rolling down a hill. When you play a game over and over, you're constantly tweaking your strategy, right? You're trying to do just a little bit better each time. What you're really doing is trying to lower your regret. And that process, that learning, naturally pulls you down to the lowest point in the landscape, which is, you guessed it, the Nash equilibrium. This even explains a simple game like rock, paper, scissors. Think about it. There's no single best move, right? If you always play rock, you're going to get crushed by paper. The stable point, the spot with zero regret, isn't one choice. It's a mix. Playing rock, paper, and scissors, each exactly 1/3 of the time.
So why does that 1/3 mix work? It's because when you play that perfectly random mix, you become completely unpredictable. There is no way for your opponent to exploit a pattern. From your perspective, you're now indifferent to what you throw next. No single choice gives you an edge. Your potential regret is zero, no matter what you do. You've found the flat, stable center of the landscape.
But, and this is a huge but, just because an outcome is stable doesn't mean it's good. There's this concept called the price of anarchy, and it's a way of measuring just how bad an equilibrium can be. It's the gap between the stable outcome and the best possible outcome for the whole group.
Let's go right back to our prisoners. This chart just lays it out so clearly. The best possible thing for the group, the optimal outcome, is for them both to cooperate. Total jail time, just 2 years. But the stable Nash equilibrium, where rational choice leads them, that's where they both betray, for a total of 10 years in prison.
The stable, rational, locked-in outcome is 5 times worse for the group than the cooperative one. That gap, that factor of 5, that is the price of anarchy for this game. It's the measurable cost of everyone acting in their own self-interest.
Okay, so if we understand this strategic landscape, this whole geometry of regret, that opens up a really fascinating question. Can we do more than just analyze the games we're in? Could we actually shape them?
The answer is yes. And it's a whole field called mechanism design. You can think of it as reverse game theory. Instead of taking a game and finding its stable point, you start with the outcome you want, and then you design the rules of the game, the incentives, the payoffs, to make that outcome the Nash equilibrium. You're literally reshaping the landscape of regret to guide rational people to a better place.
So let's just pull this all together. The geometric truth is this. A Nash equilibrium? That's just the point where everyone's regret is zero. How we learn to play a game? That's just us rolling downhill on the regret landscape. The price of anarchy? That's the gap between the low point for one person and the low point for the whole group. And mechanism design, well, that's the art of becoming the landscape architect yourself.
And that really leaves us with a final, powerful question to think about. If we can actually understand the geometry that shapes how we interact, and we have the tools to reshape that landscape, to design systems where my own self-interest naturally lines up with what's best for everyone, what kind of better worlds, what kind of better systems could we even begin to design?